We interact with table salt every single day. We sprinkle it on our food and we dissolve it in water, consuming it without a second thought because it is incredibly stable and safe. Yet this mundane substance is forged from two violently hostile ingredients: sodium, a metal that explodes upon contact with water, and chlorine, a highly toxic, corrosive gas.
If you look closely at the microscopic behavior of matter, you'll find that elements are driven by a single, overriding motivation. They are constantly trying to achieve absolute stability. In the atomic world, that stability has a very specific definition. It means having an outermost layer, the valence shell, that is completely full of electrons. The elements that naturally possess this trait are called the noble gases, and they represent the standard for atomic perfection. This table shows the electronic configurations of elements, revealing why noble gases are so stable. Helium has a full outer shell of 2 electrons. Neon completes its shell with 8, and argon does the same. With full shells, they show almost no chemical activity. But the noble gases are the exception. Most of the table, metals and nonmetals, are reactive because they're mathematically incomplete. Looking further down, sodium has just 1 outermost electron, and chlorine sits at 7. Neither has that perfect count. This inherent imbalance creates a constant tension. Elements with partially full shells will actively, and sometimes violently, interact with one another in an attempt to hit that stable number. This microscopic drive to complete a shell serves as a fundamental mechanism behind chemical reactions, pushing reactive elements toward the stability of a finished configuration. To see exactly how they solve it, let's look at sodium. Its electron configuration is 2, 8, and 1. That single electron in the outermost M shell is a point of vulnerability, separating the atom from the perfectly stable full L shell sitting right beneath it. The most efficient way for sodium to achieve stability is to get rid of it. The atom sheds the outer particle, exposing the complete octet. But losing an electron has a strict mathematical consequence. The nucleus still has 11 protons, but there are now only 10 electrons orbiting it. That leaves the atom with a net positive charge, transforming it into a sodium cation. In nature, that discarded electron cannot exist on its own. It must find a new host. That's where chlorine enters the picture. Chlorine has exactly 7 electrons in its valence shell. It needs to acquire just 1 more electron to reach the stable target of 8. When the discarded electron comes close enough, the turbulent chlorine atom captures it. The extra particle snaps in, instantly locking it into a symmetrical configuration. Because chlorine just absorbed a negatively charged particle, it now has more electrons than protons. It gains a unit negative charge and becomes a chloride anion. Now the universal laws of physics take over. You have a newly positive sodium ion and a newly negative chloride ion sitting right next to each other. Opposites attract, and they are immediately pulled together by powerful electrostatic forces. This trade solves the instability of both atoms at once. By exchanging that single electron, they lock together into a single stable entity, sodium chloride. That exact 1-to-1 exchange works perfect for sodium and chlorine. But the math gets more complex when an element has more than a single electron to discard. This formula illustrates magnesium. With a 2-8-2 configuration, it must release 2 electrons. But the middle formula shows a chlorine atom only accepts 1. To balance the ledger, magnesium reacts with 2 separate chlorine atoms, offloading 1 electron to each. This multi-atom negotiation results in the formation of a brand new compound, magnesium chloride. Whether the transfer involves 1 electron or several, any compound forged by this complete transfer from a metal to a nonmetal is known as an ionic compound. The electrostatic forces that hold these oppositely charged ions together are unyielding. They lock the atoms in place with immense strength. And those forces don't stop at isolated pairs. A positive ion will attract negative ions from all sides, and those negative ions will attract even more positive ions in every direction. These microscopic bonds multiply exponentially. They stack together into perfectly ordered, massive geometric structures, building the rigid crystal lattices that form the solid world. The complex, tangible materials we interact with every day represent the successful conclusion of these atomic trades, mathematical stability scaled up into the materials that define our physical reality.